I don't prepare anything for these sessions. The problems are supposed to be your problems. Me, I have no problems with set theory, right? It's okay, Mostovsky-Shepardson collapse function. So what have we got? So that said, if HR, and we had here an R that was well-founded, and it was extensional, so it behaved a little bit like epsilon. If I had U and V in H, and U is different from V, then there is some W in H where R differentiates between these two, U and V, not W. Then you could just know that this was isomorphic to something. And there was a unique transitive set here that it was isomorphic to. And a unique Pine isomorphism. So if there's a unique isomorphism, its range is this, so this is unique. So that's unique as well. And what can we say about the map? The map is forced upon us what pi is. If this is going to happen, then so if this is to happen, so then we must have what did I say? Pi of V is the collection of pi of U's, where U is in H and U is R below V. This is basically what must happen. And you can see what we end up with, right? We end up with that U becomes below V if and only if pi of U is a member of pi of V. And that's just corresponding to the fact we want this relation here to correspond to the epsilon over there. Now, actually, I don't particularly want people to get kind of too hung up on this this lemma and spend, you know, hours and hours and hours studying, because we're going to use it just in one or two crucial places. We're not going to spend a lot of time analyzing how it works. But for example, suppose I just took the evens and I took less than. Right. So I should, let me try and make it look like the above. H is my set of evens, and my R is less than. So here's my H, and here's my R. So you can start puzzling out what's going to happen. R is well-founded because it's just less than on these natural numbers, so that's well-founded. But also, it's extensional in a kind of trivial way. Well-founded. Because this is a well order. of the evens, which are just contained in omega. It's also extensional. Suppose I take, in a kind of trivial way, right? I take any two even numbers. As I take 2, this is different from 4, right? These are both in evens. And what do we have? I want something that's in 4 but not in 2, right? Or vice versa. So 2 is a member of 4. Sorry, 2 is less than 4. But 4 is not less than 2. So I've got that this R here is extensional. Okay, so now I apply the collapse. I mean, do you want to guess what happens? I mean, all that happens here is that this just goes to omega less than, which of course is just epsilon here. So one can just check that, well, pi of 0 is 0, the empty set. What is pi of 2? Well, pi of 2 is a set of pi of things which are in the domain and come before 2. Right, so this is just the pi of v's, such that v is in evens and v comes before, sorry, less than 2. So it's just pi, the set containing pi of 0. So it's just this, which is 1. And if you carry on this analysis a bit further, pi of 4, you'll find out it's just pi of 0 and pi of 2. So this is 0, 1, and that is 2. Okay, so it's a kind of toy example of the Mostovsky-Shepardson collapse. So indeed, pi of 2k just ends up being k. So very, very much a toy example, because this, after all, is a well ordering. It's not just a well-founded partial order, it's a well ordering. So the evens will collapse to the naturals. And if you try it with the odds, of course, they collapse to the naturals as well in the same way. So, and indeed, but this is entirely what one would intuitively think. After all, what is isomorphism? You know, it's Greek, it means the same shape. And this has got the same shape as this, right? It's a whole load of dots strung out in a row where it's epsilon. And here we have the evens strung out in a row with this less than. So these are not necessarily surprising. So these kind of toy examples are kind of quite simple. So I said I think one of the exercises suggests you think about what happens when this is not extensional. If H and R, say here, is well-founded, but not extensional, then what can happen? Well, it's not going to be an isomorphism. Right? I can define I could still define pi of v to be this, pi of u's for u in H, and u is below v. Okay, so pi is still going to be onto whatever the range, whatever its range is. So pi is onto its range, right, which kind of doesn't need saying almost. And it's preserving the R, taking it over to epsilon. So what must fail is that it's, in general, it's not going to be pi 1, 1. It's not going to be 1, 1. So if it is not an isomorphism, it must fail to be pi 1, 1. It must fail to be 1 to 1. So one can think of something like this. So let's think about something that's not extensional. So why I could take the evens. Yes. So let's look at the evens. But now we join to the evens this set here. So what have I got? I've got that 2 isn't even. So let me call this H. This is my H, and my R is going to be epsilon. Okay, 2 is different from this thing here. Remember that 1 is just, I'm maybe already making this too complicated. This is the empty set here. And what is 2? 2 is 0, 1. So I'm making I'm making this too complicated. I'm just trying to think of an example of two sets using simple things, which will ensure that we've got non-extensionality, but I just want them then to collapse to something nice. So I hadn't prepared an example. So if one said, suppose I consider 2, 4, 6. So here are the evens without 0. Here. And maybe I throw in 1 here. Or I just throw in 1. Yeah, maybe this works. Yes, okay, let me write it out again. So this should be all right. So these bits over here aren't relevant. Let me drop these. So if I call this H, right? And I look at H epsilon. So it's kind of silly. It's just got 2 things in it. But the point is that 1 is different from 2. Well, the singleton one. This has got an element 1 in it, right? And this, well, 1 is an element of 2, but okay, this. Let's take this. So now if you apply pi to this, right, what is pi of 1 going to be? It's a set of pi of v's such that v is in H and v is a member of, here's my relation R, v is a member of H. Right. Sorry, v is a member of 1. V is a member of H and V is a member of 1. Okay, so there's nothing in H that's in 1, right? The only thing here in 1, in this singleton 1 is 1, but 1 is not a member over here. So this is just 0, the empty set. Now, by the same reasoning, pi of 2 is also the empty set. So this is a kind of silly example of 2-element H, which when you do the Mostovsky-Shepardson collapse, it just collapses everything to 1. To the set containing the empty set. So non-extensional, two objects get sent to the same point. So it's just a little example of that happening. Okay, any questions there? Want me to go through anything about stationary sets again or not? Diagonal intersections.
Rupert's put a message in the chat about going over something to do with stationary sets. Yeah.
Oh, sorry, I forgot to open the chat. Sorry, Rupert. Going over stationary, okay, fine. So a stationary set is a semi-thick set. So entirely non-standard nomenclature there. It's just me making it up. It has no official standing. So if I take S, and I'll write down here stationary in omega, where this is a regular cardinal. I don't know whether I counted omega as itself a regular cardinal. Maybe it does. So maybe I should say that big omega is uncountable. Makes no sense really to talk about stationary subsets of little omega. Then the definition says S intersect C is not empty for any CUB C contained in omega. And again, I'd sometimes just write CUB under there. So these guys are very thick. And to be stationary, all you have to do is hit every CUB set just once in one place. But actually, as we saw, if S is stationary, S intersects C is not just one element, but there are big omega, many of them. But is itself stationary. And the reason was that the intersection of two CUB sets is CUB. Two CUB sets, D and D prime contained in omega, is itself CUB. Because then we could reason, as in the exercise 212, right? I take S and C, where S intersects C, and I take any other CUB in there. And then I'll just get that S intersect C intersect D is S intersect C intersect D. And this is I now appeal to the reason, this is CUB, this is stationary, so this is non-empty. So S intersect C is stationary because D is arbitrary, or some any other D that was there. So the picture would be, you've got omega here, you've got this semi-thick S. And if I've got any very thick C here, S intersects C, it coincides in a lot of places. In fact, it coincides in stationary many places. So a stationary set kind of weaves its way through all closed unbounded sets. And then we saw easily S intersect S star is stationary. Right, so this is just the limit points of S. Right, S needn't be closed. There may be a whole bunch of elements of S below some mu, and mu may or may not be in S. But what this says is that some mu's, some limit points are going to have to be in S, because some limit points intersect the stationary set. I get enough limit points of S are in S for this to be stationary. So S must contain its limit points very often, but it needn't contain them all. So it must contain its limit points very often. But not always. Of course it would if it was closed, because what is closure? It says that S star will be contained in S if it was closed. So we had examples. We looked at the points of cofinality omega 1 below omega 2. So if this is omega 2 and here is omega 1, I'm interested in points below omega 2 here, alphas, which can only be approached by omega 1 sequences. Now, if I take an omega limit of points like this, an omega sequence from S omega 1, its limit up here has got cofinality, well, omega. So it's not going to be in S omega 1. The sup here cannot be in S omega 1. By definition of what it is. Right? So this is a stationary set which contains very often its limit points. Indeed, any limit point which has got cofinality omega 1 by definition, but it omits also very many of its limit points, namely all those of cofinality omega. So no beta in this S omega 1 star, with the cofinality of beta being omega here, can be in S. Just by definition. Stationary sets can be, well, disjoint as well, and this provides an example of this. So we can have two stationary sets, S1 and S2, contained in some omega, with S1 intersect S2 being empty. So it's a kind of slightly strange situation. A stationary set must meet every closed unbounded set, but they can be entirely disjoint from each other. And we have the example. Shows this again. I take A omega as omega 2, and we look at S omega 1 and S omega. So these were the points of less than omega 2 with cofinality omega 1, and this is the set of points less than omega 2 whose cofinality is omega. Both of these are stationary, but of course they're disjoint. But empty intersection. So the remarkable argument of Sullivan and others is that you could take any stationary set in some irregular cardinal here, take any S here stationary, and actually you can just kind of divvy it up. You can divide it up into, partition it into, well, two disjoint stationary subsets. Any such S up into S0 and S1, where they're disjoint, but their union is all of S. So this one is stationary, and we can have these stationary as well. So I can always partition a stationary set into two disjoint stationary subsets. But the remarkable argument due to Sullivan is that I can take this S, I can pick any gamma less than omega, and I can partition this up into gamma many disjoint stationary sets. I mean, you might like to think about how to do this just into two. It's not trivial. Right? It's quite tricky to think about this, but this is much harder. For any gamma less than omega, we can partition. And partition is usually the word that means into different pieces whose union is the thing you start with. Into these S alphas, for alpha less than gamma, where they're all disjoint. Intersection of any two, S alpha prime is empty. The union of them all is S. And still these are semi-thick. And each alpha is stationary. So that's quite a that's kind of tricky to do, right, on the whole. But you know, you can find that in any textbook on set theory. But because it's tricky and we don't have any use for it, I didn't include it in the notes. Sorry, I should keep looking at the chat. What's that word you've written, for any Sullivan. So he was one of the, he's still alive, he's quite elderly. I mean, I reckon in the late 60s and 70s, I mean, there were two great set theorists. Jensen, who has his photograph in the notes, and Sullivan, oh, I think his photograph is in my notes as well, right? So Sullivan was at Berkeley, and Jensen was in the university in Bonn, and they were, I mean, really fundamental in expanding set theory in the late 60s and 70s. Sullivan was, he had a result that, you know, you can quote to mathematicians, which is quite, quite quotable. So Sullivan, he proved that it was consistent with the axioms of ZF that every set of reals was Lebesgue measurable. So for every set of reals contained in the R had a Lebesgue measure. Now, I mean, if you don't know what Lebesgue measure is or measurable sets, this won't mean too much to you. But if you do, if you're an analyst or a probabilist, such people, they worry about sets they define, subsets of the real line that they define, and you can't assign, you know, a length to them, or subsets of the plane, you can't assign an area to them. They're not measurable. So that's kind of too complicated to assign a measure to. But actually what Sullivan showed was we needn't worry. We could, with our axioms, we could consistently assume that every set we can find actually has a measure associated to it. And we still wouldn't get a contradiction if we made that assumption. So this was a paper in the Annals of Maths, and there was a lot of talk about this. So this would have been, yeah, this was late 60s, I think, this. So he assumed then mathematicians would start assuming that every set was Lebesgue measurable, and they wouldn't worry about this anymore. But in fact, that wasn't the case. They still worry about whether sets are Lebesgue measurable or not. So it's kind of an interesting sociological phenomenon in mathematics as well. Right. So that's Sullivan. Anything else you want doing? Okay, I'll just do an exercise. 2.9. I mean, this is more to kind of show how to set something out. Right? and a chance to explain the Beth function again. So this is Hebrew Beth, B in the alphabet. This is the V hierarchy. So recall how we define the Beth numbers. This is omega or Aleph 0. And Beth alpha plus 1 is 2 to the power Beth alpha. And then we look at the V hierarchy. So I shouldn't need to say this at this stage. And it limits, it's the union of the previous V's. So it's about the size of these V's. And the clue here is that each level is the power set of the previous level. And here, Beth alpha plus 1, it's the size of, well, the power set of Beth alpha. Here. So one just shows by induction on alpha that this holds. Okay, is there any questions about the setup? Now there's this little wrinkle here because it doesn't say, for example, that the size of Vn is Beth n, right here. Or more dramatically, if alpha was 0, the size of V0 is Beth 0, because Beth 0 is omega, and the size of V0 is just 0, it's the empty set. So it's because the numeration starts kind of omega off at the beginning. Beth 0 has got size omega, whereas V0 has size 0. And all this omega plus alpha does is just redress that balance, or that imbalance. So I guess the solution here is you just say by induction on alpha. Right, so there's no need to write lots here about this. So when alpha equals 0, what is V omega? It's the union of the Vn's here. So each of the Vn's is finite. V0's got size 0. The size of V1, collection of the power set of, right? So 2 to the power 0 is just 1. Right? And then the size of V2 is the size of the power set of V1. So 2 to the power 1, which is 2. So the Vn's are all finite. So these are all finite. And indeed, if you check it out, the size of Vn is 2 to the 2 to the 2, like this. And I think altogether there are maybe n minus 1 twos here. something like that. I mean, one can calculate what the size of the VNs is. Okay, so this here is countably infinite. Here, it's just omega many finite sets. So it's got size omega. And this is Beth 0. So that's okay. V omega plus 0 equals this, is Beth 0, which is just what we want here. V omega plus 0 is Beth 0, which is omega. So assume as an inductive hypothesis that V omega plus alpha has got cardinality Beth alpha. Let's suppose we've proven that. Then the size of V omega plus alpha plus 1. So recall, this is just the power set of V omega plus alpha. So this is going to have the size of the power set of V omega plus alpha. So that's 2 to the Beth alpha. But that's what we define to be Beth alpha plus 1. So yet again, here I've got alpha plus 1, here I've got alpha plus 1. So the successor stage works there. So, I mean, 3 stages to the induction, alpha equals 0, alpha a successor, and now when alpha is a limit. So if for alpha less than lambda, lambda a limit, then recall that V omega plus lambda is the union of the V alphas, alpha less than lambda. Sorry, I got alpha. Sorry, alpha less than lambda here. So now I've already got it. I've got here then the size of V omega plus lambda is the size of this. So this then is going to be the sup of these Beth alphas here, and this is just Beth lambda. So the limit case works here as well. So that will be how you could set out a proof by induction there for that. Once the alpha has got a little bit large here, it absorbs by ordinal addition the omega that's there. So aside, not relevant really to this, omega plus omega squared, right, actually is just omega by laws of it's just omega squared by laws of ordinal arithmetic. I can just say this here is omega lots of 1 plus omega by distributive law. Omega plus omega squared. But 1 plus omega is just omega. I'm just putting one more dot on at the beginning here. So this is just omega times omega, which is this. So once alpha is bigger than or equal to omega squared, right, I've got that omega plus alpha is just alpha. So V omega plus alpha is just this. And I don't have to fuss about the little omega plus there at the beginning. So for alpha bigger than omega squared, I've got the size of V alpha is Beth alpha. And I don't have to worry about that omega plus anymore. Okay, anything else you can do? Right. Okay then. I hope. Let's see. Let me look at you earnestly in the face. So let's hope this. I hope these sessions are useful to you. That's all. So keep the questions coming. I mean, if there's anything that, or any way that these could be, I could do something better than this. I feel like I run out of things to say and I just start doing some exercises. And maybe that's good, right? But maybe there's a better way of doing this that you would prefer. So do feedback, right? Okay, good. Monday's lecture's already uploaded actually on the site, so you can start there. I hope you saw my email as well about, there were some requests on the early questionnaire to have more time for exercises. So I've delayed the handing in of exercises to Fridays. So we'll set it on Fridays about the previous week's work rather than setting up Mondays about the work to come. That's the way it is. I only thought you might get a quicker turnaround that way, but let's stay with the way. I used to do it on Fridays. Okay, great. Well, as great as the technology allows. Good, I'll see you next week then. Okay, have a good weekend.